Hello, my name is Dr. Darren Ong Chung Lee. I write my papers as Darren C. Ong, and I'm going to present on quasi-periodic music. I'm from Xiamen University, Malaysia, in Sepang, in Selangor. So this presentation will have two parts. In the first part, I will discuss this concept of aperiodic order, which is the mathematical pattern which I study in my research. And in the second part, I will talk about music and how this aperiodic order, which is a mathematical concept, can be connected to music theory in that it gives us a way to convey infinity in a way that musicians find interesting, in the way that music theorists find interesting. So let's first discuss this concept of aperiodic order. So aperiodic order is not mathematically precise, at least the way that I use it in this talk. So I use it to refer to terms that are not periodic. That's what aperiodic means. So aperiodic means not periodic. But it's still ordered. It still has structure. And the kind of structure it has is that these patterns are somehow as close to periodic as possible in some way. So let's look at a continuous example. So Fibonacci word, we consider it as a discrete example of aperiodic order. But we also have this idea of a quasi-periodic function. This will be the main topic of our talk. So an aperiodic function can be, here's an example of one. Fx equals cosine 2 pi x plus cosine x. And this will be actually the function that we will inspire the rest of the talk, so maybe good to pay attention to it. So we can check that this function is not periodic, and it's quite easy to. You plug in x equals 0, you get 2, because you get cos 0 is 1 and cos 0 is 1. But you will never ever achieve another 2. There is no other x for which fx equals 2, and this completely rules out the possibility that fx is periodic. It can't be periodic, so it's aperiodic. But you can see that it's also really, really close to periodic in some way, right? And you can see it from the graph of this function. It never reaches 2, but it gets arbitrarily close to 2. And you can see that it looks very close to periodic, even though it's not, because it never reaches 2 again. But where does it reach 2 first? Well, for example, when x equals 6, right? Because 6 is very close to 2 pi. So whenever you have an integer that's close to a multiple of 2 pi, you get something that's almost a period, right? Because, for example, 6, you get, it's almost 2 pi. So it doesn't exactly get to 2, but it gets really close to 2. So it almost seems like this function has period 6, but it does not. Yeah. So here's an example. So this is a really interesting example when you have two periodic functions, but one period is rational and the other period is irrational. You get a pattern like this that doesn't quite repeat, but almost does. So this is another example of aperiodic order, because you have a function that's not periodic, but it is very, very, very close to periodic in some way. Yeah, and you can make this mathematically precise, but I will choose not to for the context of this talk, because it's not that important. So why do we care about aperiodic order? So there's actually a physics reason behind this, and it's because of these objects known as quasi-crystals. So they have received a lot of attention recently because the discovery of quasi-crystals won the 2011 Nobel Prize in Chemistry to Dan Shechtman. So it's a novel material, it was newly discovered, it appears in nature, but it can also be synthesized. So it's like a crystal. So crystals have a periodic atomic structure, but quasi-crystals have aperiodic atomic structure. So you can see here that there's a 10-sided rotational symmetry to this quasi-crystal structure. So this is a diffraction pattern of a quasi-crystal. And we know that for a periodic tiling, the only way to tile a plane using a periodic shape is by using a hexagon, a triangle, or a square. So this is tiling of the plane using something that's 5-sided or 10-sided, if you prefer. So it cannot possibly be periodic, right? So this is a structure that looks very close to periodic, but actually never repeats. And that's why there's been recent interest in studying almost periodic patterns, so aperiodically ordered patterns, because they are a good model for understanding these quasicrystals. I guess a really famous example of the quasicrystal is the Penrose tiling. Not the quasicrystal. Another famous example of aperiodic order is the Penrose tiling. And you can see that there are similarities here, because the Penrose tiling is very much based on 72-degree angles, and so is the rotational symmetry of this quasicrystal structure, 72 degrees. Yeah, and Penrose tilings are maybe a good idealization of what the quasicrystal atomic structure looks like. So clearly these aperiodic patterns are very beautiful, and they inspire art in many ways, and I think they can also be used in music. And there's a strain in music that tries to convey the concept of infinity. Music is of course finite, you can't play a piece forever, but musicians and composers have sometimes tried to grasp this idea of infinity in different ways. So that's, in my paper I go through many different examples, but I think for this presentation I'll only give one since it's such a short amount of time. I'm not going to try to pronounce this French title, but this is a French composer who created this piece of music. The English translation is Quartet for the End of Time, right? And you can see here already from the title that Messiaen was trying to convey this idea of infinity. And we look at the first movement of this piece, the Liturgie de Cristal. So I guess before we talk about it, let's just go through the quote first. So Liturgie de Cristal, I'm just going to go through this quote from this Christopher Dingle, who wrote a book about Messiaen. It is undoubtedly the most famous example of a compositional machine in Messiaen's music. The piano part has a cycle of 29 chords, with a set of 17 durations, and because 29 and 17 are prime numbers, right? So there's a pattern of like a cycle 29 and a set of 17. So when they take them together, it takes 17 times 29 cycles to return to the same starting point. So it sounds like forever. And then you add a cello, which has a cycle of 5 pitches and 15 durations. So you have 15, 29, and 17, which are all relatively primed, and that means that all these different parts of the quartet, it takes a very, very long time for it to repeat, right? Because it takes many, many cycles for it to repeat, and this is due to the relative primality of the periods, right? 15, 17, 29. And in fact, the way that Messiaen composes it, if you want to return to a starting point, it would take 4 hours and 40 minutes, but in the piece, we only present a short fragment. So it teases the idea of infinity. This piece of music teases the idea of infinity, but it's not actually infinite, because you have to wait 4 hours and 40 minutes, but it does go back to the start again, right? Because when you can multiply these relatively prime numbers to get a huge number, but eventually, the pattern does repeat again. So I'll play a short clip of Liturgie de Cristal, so you can notice how we have these different parts with different periods combining with one another to create this illusion of infinity. So inspired by Messiaen's music and this attempt to convey infinity. So again, it's not just about Messiaen, not just about the Liturgie de Cristal. There's actually been a lot of musicians who try to convey the idea of infinity. So let me talk about Raindrops in A minor. And this was again inspired by the quasi-periodic function, fx equals cosine 2 pi x and cosine x. So again, these are two functions added together but one has a rational period, 1, and the other has an irrational period, 2 pi. So inspired by that, I decided to create a piece of music in 2 parts, where one is takes a rational number of seconds and repeat it, right? And the other one takes an irrational number of seconds to repeat. So it's a very simple piece of music just to illustrate the concept. But compared to what Messiaen does, which he takes patterns of he uses primality to create like long patterns that long repetitions, by using repetition where one period is an irrational multiple of the other, where we in fact do create an infinite musical composition, right? So this is truly infinite, whereas Messiaen, for example, only was able to create an illusion of infinity. So maybe let's take a listen. Anyway, thanks for listening, and I just want to give thanks to the Messiaen University Malaysia for funding this research, and also the Malaysian Ministry of Higher Education for the FRGS grant. And here's my grant number, and here's my DOI for the paper if you want to see the paper. You can also find it on my website, www.drong.my, or you can scan this QR code. Thank you.